Welcome to Foundation Mathematics, Integration, the fundamental theorem of calculus, antiderivatives, and area under a curve. The objectives for this session are to understand and apply the fundamental theorem of calculus and find antiderivatives, and recognize the integral as the area underneath the curve of a non-negative function. Recall the rule for differentiating x to the power n. If y equals x to the power n, then dy dx equals n times x to the power n minus 1. The reverse of differentiating is integrating. And the rule for integrating x to the power n is if dy dx equals x to the power n, then y equals x to the power n plus 1 divided by n plus 1. Integration is the reverse of differentiation. So what do we do if we want to differentiate? We start with, say, x to the power n. We multiply by the power and then subtract 1 from the power to give n times x to the power n minus 1. And what do we do if we wish to integrate? We start with, say, x to the power n, then add 1 to the power, and then divide by the power, so that we are left with x to the power n plus 1 divided by n plus 1. X to the power n, or x to the power n plus 1 divided by n plus 1 is the function, and the gradient function is respectively either n times x to the power n minus 1 or x to the power n. Now, integration is the reverse of differentiation. Before we go into any more details, let's take a look at 3 more examples. Y equals x cubed plus 6, y equals x cubed, and y equals x cubed minus 1. All 3 functions are different. However, when we differentiate, we obtain dy dx equals 3x squared for each of them. So when differentiating, constant terms disappear. Functions which only differ by a constant differentiate to give the same function. Therefore, when we integrate, we must add a constant of integration at the end of a function. So when we integrate dy dx equals 3x squared, we obtain y equals x cubed plus c. And notice here we've added a constant of integration. So if f dash of x equals x to the power n, then f of x equals x to the power n plus 1 divided by n plus 1 plus c, where of course n does not equal minus 1. Let's take a look at integrating x to the minus 1. We cannot use this rule that we've indicated here if n equals minus 1, since 1 over n plus 1 is undefined at n equals minus 1, as we cannot divide by 0, as you can see from these formulae. We will look at how to integrate x to the minus 1 in a later session. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are going to apply the highlighted rule to our example. So we now have x to the power 6 plus 1 divided by 6 plus 1. And of course we must add the constant of integration, c. Here's the value n plus 1. And this becomes x to the power 7 divided by 7 plus c. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Again, the rule which we are applying has been highlighted. So n plus 1 is a third plus 1. And tidying up gives us x to the power 4 over 3 divided by 4 over 3 plus c. And when we're dividing by fraction, we multiply and flip the flat fraction over. So we're now left with f of x equals 3/4 x to the power 4 over 3 plus c. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Before we begin, remember that when integrating polynomials, apply the rule for integration separately to each term. So dy dx equals x to the 4 plus 3x squared minus 4x to the minus 3 over 2 implies y equals x to the 5 over 5 plus 3x cubed over 3 minus 1 minus 3 over 2 times 4 times x to the power minus 3 over 2 plus 1 plus c, which tidies to x to the 5 over 5 plus x cubed plus a half times x to the power minus a half plus c. Now let's take a look at indefinite integrals and some notation. The symbol in red, which looks like an S which has been stretched, represents the integration process. So integral f dash of x dx equals f of x plus c. So for example, the integral of x to the power n dx equals x to the power n plus 1 divided by n plus 1 plus c. So this elongated s means integrate. X to the n in this example is the expression which we need to integrate, and dx means integrate with respect to x. When integrating a polynomial, we can integrate terms one at a time. So integral of f of x plus g of x dx equals integral of f of x dx plus integral of g of x dx. Pause the video and have a go at example 4. Press play when you're ready to view the solutions. You are required to integrate the expression on your screen. So let's solve this. We are going to integrate term by term. So the integral of x squared becomes x to the 2 plus 1 divided by 2 plus 1. And the integral of minus x to the power 2/3 becomes minus x to the power 2/3 plus 1 divided by 2/3 plus 1. And if we tidy up, we obtain x cubed over 3 minus x to the power 5 over 3 divided by 5 over 3 plus c. And tidying up some more, gives us x cubed over 3 minus 3/5 x to the power 5 over 3 plus c. Now have a go at this example. Pause the video and have a go. Press play when you're ready to view the solutions. You are required to integrate the expression shown on your screen. So let's solve this. This integral can be expressed as 3x to the minus 2 minus 4x to the minus a half. And integrating gives us 3x to the minus 2 plus 1 divided by minus 2 plus 1 minus 4x to the minus a half plus 1 divided by minus a half plus 1 plus the constant. And tidying up, and tidying up some more, gives us minus 3x to the minus 1 minus 8x to the half plus c. The rule for integrating kx to the power n is that if f dash of x equals k times x to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. Let's now take a look at definite integrals. If f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals f of x between the limits b and a, which equals f of b minus f of a. An integral between two limits can be calculated and is called a definite integral. Recall that an indefinite integral produces a function, and a definite integral usually produces a value. This result is also known as the fundamental theorem of calculus. Let's now take a look at the steps for integrating definite integrals. First, write the definite integral statement with its limits. So, for example, integral from a to b f dash of x. Then integrate and write the integral in square brackets. So, f of x is between square brackets between the limits b and a. Evaluate the integral by working out f of b minus f of a. Let's now take a look at an example. Let f dash of x equal 4x cubed. We will find the integral of this function between limits x equals 2 and x equals 5. Now the integral from 2 to 5 of 4x cubed dx here from x equals 2 to x equals 5 gives us x to the 4 between the limits 5 and 2, as shown. And this is equal to 5 to the 4 minus 2 to the 4. And working this out gives us 625 minus 16, which equals 609. The area of the curve can be found using definite integration. Consider a positive curve y equals f of x and define the area under the curve to the left of x as a function a of x. So here's our curve, it's positive. Consider the point x and the corresponding point where it meets the function at f of x, and the area under the curve to the left of x, which is denoted by a of x. Now if x increases by a small amount, say delta x, the area now changes to a of x plus delta x. As x increases, the area a of x also increases to a of x plus delta x. For a small increase in x denoted by delta x, area increases by the amount delta a, which equals a of x plus delta x minus a of x, as shown in the diagram in blue. Now the change in area is approximately rectangular. So as delta x is made smaller, any error will be insignificant. Therefore, delta A is approximately equal to the width times the height of the rectangle. In other words, delta x times y, or y times delta x. And if we rearrange this, we obtain delta A delta x is approximately equal to y. Now if we take the limit, so as delta x tends to 0, we obtain dA dx equals y. And integrating gives us a equals integral of y dx. Now the area between a positive curve, the x-axis, and lines x equals a and x equals b is area equals integral from a to b y dx, where y equals f of x is the equation of the curve. So diagrammatically it will look something like this. We've got a positive curve, f of x, and we've got limits a and b, and we've got the shaded area in yellow beneath the curve. Let's take a look at an example. Find the area of the finite region between the x-axis and the curve y equals 15 minus 2x minus x squared. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. If we factorize this function, we obtain 3 minus x times x plus 5. The intercept with the y-axis is 15. And the curve crosses the x-axis at x equals 3 and x equals -5. Therefore, if we're wanting to find the finite region between the x-axis and the curve, we're looking for the region between -5 and 3, which is below this curve. So area equals the integral from -5 to 3 of 15 minus 2x minus x squared dx. And so integrating this term by term, we obtain 15x minus x squared minus x cubed over 3. And then putting in the limits, so x equals 3 here, and x equals -5 here. And then tidying up, gives us 8 1/3. This brings us to the end of this session. If you have understood its contents, you should be able to understand and apply the fundamental theorem of calculus and find antiderivatives, and recognize the integral as the area underneath the curve of a non-negative function. Thank you very much for listening.